हेलो दोस्तों, welcome to my channel. So today we will see how to design a slab manually. How to design a slab manually. I have one simple PDF. In this PDF we will show how to design a slab manually with this. As you can see, the whole PDF calculation is there. So after that, we will design the slab in Excel also. Okay, so let's start with this. In first design of slab, this is a general. A slab is a flat and two-dimensional planar structure element having a thickness small compared to its other two dimensions. As you know, it provides a working flat surface or a covering shuttering in the building. In primarily transfer the load by the bending in one or two directions. Reinforced concrete slabs are used in floors, roofs, and walls of buildings and decks of bridges. The floor system of a structure can take many forms in cast in situ solid slab, ribbed slab, or precast units. Slab may be supported on monolithic concrete beams, steel beams, walls directly over columns. Also, the concrete slab behave primarily as the flexural member and design is similar to that of the beam. इसका कहने का मतलब ये है कि हम स्लैब वो जो हमारा है ना उसके दो डायरेक्शन बड़ी होती है और एक डायमेंशन छोटी होती है। जैसे कि हमारी कोई प्लेट ही समझ लो, अगर प्लेट की लेंथ और विड्थ ज़्यादा होगी पर उसकी डेप्थ कम होगी लेंथ और विड्थ के मुकाबले, वो हमारा एक टाइप का स्लैब ही हुआ। स्लैब का इस्तेमाल हम ब्रिज में कर सकते हैं, हमारे घरों में होता है, हमारा घर का कंस्ट्रक्शन जब होता है उसमें स्लैब होता है। और स्लैब के दो टाइप है, वो भी हम देखेंगे क्लासिफिकेशन। सो फर्स्ट वी विल सी क्लासिफिकेशन ऑफ अ स्लैब. Slab are classified based on the many aspects, like based on the shape, based on the type of the support, based on the support of boundary condition, based on the use, based on the cross section of the sectional configuration, and basic span directions. First, we will see based of the shape. In particular classification, there are the many uh, subdivided classification. In that, the square slab, rectangular slab, circular slab, and polygonal in shape slab. Also, second classification is based on the type of support. Which type support is there in the slab? First, slab supported on the wall. Second type is a slab supported on the beam. Third type is a slab supported on the column, means it's called as a flat slab. Also, third classification is based on the support or boundary condition. In that, the first classification is a simple supported, cantilever supported slab, overhanging slab, or fixed continuous slab. Next classification is based on the use. First classification is a roof slab, flat slab, foundation slab, water tank slab. Also, fifth classification is based on the cross section or sectional configuration. In that, it cover the ribbed slab or grid slab. Both are same. Also, next is a solid slab, filler slab, or folded slab. Next, sixth classification of the slab is the basics of a slab spanning direction based on the slab span direction. This is the main type of slab. In that, one-way slab spanning in the one direction only, and second is the two-way slab spanning in the two directions. In general, the rectangular or one-way or two-way slab are very common, are discussed in the detail. Here we saw that one-way or two-way slab design. Next is the our methods of analysis. The method of slab is extremely complicated because of the influence of the number of factors stated above. Thus, the exact closed form solution are not easily available. The various methods are for analyzing the slab is a first method is a classical method. Second is a yield line analysis. Third is a numerical techniques, and fourth is the semi-numerical techniques. Fourth is the semi-empirical techniques. In the classical method, there is a lively and linear solution plate analysis. In yield analysis, we'll use the ultimate and limit state analysis. Third is the numerical technique. In that, we will use the finite element or finite difference method. And fourth is the semi-empirical. In that, the prescribed by the codal practice design, which use the coefficient. And next is the general guidelines for the slab. As you can see, the we will if you design the slab, so you will have to consider the effective span. This is the guideline given in the code. As guideline is given in the code. Also, the effective span of the slab shall be lesser of the two. First one is a L. L is equal to clear span plus effective depth of the slab. Second is the L equal to center to center distance between the supports. And next is the depth of the slab. This is the criteria for the considering or assuming the depth of the slab. In that, the depth of the slab depend on the bending moment and the deflection criteria as per the IS code provisions. Particularly, we will use the IS code 456-2000 for the slab designs. And the trial depth we can obtain from this using uh, if you have a effective depth equal to this codal formula is also given on the our IS code. In that, the effective depth D is equal to span, means our basic span, upon L by D, basic into span given upon basic span L by D into modification factor K. We will see how to define how to find the modification factor in the next video. For obtaining the modification factor, the percentage of a steel for the slab can be assumed 0.2 to 0.5%. Next is the effective depth D of a 2A slab can also be assumed using the clause of 24.1 from the IS code 456. Provision for shorter span is if the our shorter span is less than 3.5 and loading is classified less than the 3.5 kilonewton per meter square. This is just the stable. If your support is simply supported, so you can use the D as per the 1 upon 35. If you use the steel grade of Fe 250, if your slab is simply supported and steel grade is high like Fe 450, you will have to use 1 upon 28. If your slab is continuous, you will have to use 1 upon 40. If your steel grade is 415, you will have to use 1 upon 32. This is the criteria for effective depth. Next, also this is the given this is the thumb rule for the design. For the one way, you will have to consider D equal to L upon 22 or L upon 28. Also the two-way simply supported slab, you can use D equal to L upon 20 to L upon 30. L means effective length of the slab. As we will see in the previous slide, for the effective length criteria. You will have to consider from both effective length criteria minimum length. Next is the load on the slab. How to calculate the load on the slab? For the calculation of the load on the slab, you will have to just calculate the first depth of the slab. After our slab is also RCC. For that, we will take a density of 25 kilonewton per meter square. Just you have to consider the all load coming on the slab. First load is coming from the on the slab is dead load. Second load is coming is the floor finish load, like tiles or something or fillings, etc. load is considered in the floor finish. Second is our live load. Live load means our human load or some moving or partition loads. We will design this load in this manner, load per meter square, because our slab is area quantity. So we will design as the area quantity, means load per meter square. Also we will assume the particular floor finish 1 to 2 in this particular calculation, 1 to 2 kilonewton per meter square. Also the live load we will assume 3 to 5 kilonewton per meter square. This is also depending on the occupancy of the building. Next is a detailing requirement as per the IS code 456/2000. First is the nominal cover as per the IS code. If you use mild exposure condition, you will have to give the 20 mm cover for the slab. If your exposure condition is the moderate, you will have to give the 30 mm cover for the slab. However, if the diameter of the bar does not exceed the 12 mm, you don't have the permission to use the greater dia bar after the 12 mm. If may or you have to reduce the cover 5 mm. Thus, for the main reinforcement up to 12 mm diameter or bar, and for the mild exposure, the nominal cover is 15 mm. This is the nominal cover used for the mild exposure. This is the minimum reinforcement criteria for the slab. The reinforcement in the either direction in the slab should not be less than the 15% of the total cross section area for if you use the mild steel like Fe 250 steel, and 0.12% of the total cross section area if you use the HYSD means Fe 415 and Fe 500 steel. And next is the spacing bar criteria for the slab design, and that the maximum spacing of the bar should not exceeded for mild steel. This is the 3D, or D is the effective depth of the slab, or 300 mm, whichever is smaller. You don't have to permission to exceed that spacing. For the distribution bar, the criteria is 5D or 450 mm, whichever is smaller. You don't have to exceed this small from both smaller for the spacing of the bar. D is the effective depth of the slab, as you know. Also, the note is given the minimum clear spacing of the bar is not kept less than the 75 mm. As you know, perfectly 100 mm through code do not recommended any values. If you have to perfect design, you will have to consider the 100 mm and does not use the clear spacing less than the 75 mm. As you so the 75 mm spacing is very small, or it is very complicated in the site construction of that particular slab. Also, the minimum dia of bar criteria given. The minimum diameter of the bar in the slab should not exceed the D upon 8, where D is the total thickness of the slab, not the effective. Please remember that. Next is our one-way slab. Behavior of a one-way slab. When a slab is supported on the two parallel opposite ends, as you can see in the figure, this is the two parallel opposite ends. This is the supporting of the slab, and this is the diagram of the deflection diagram of the particular slab, and this is the moment diagram of the particular one-way slab, and it the span only in the direction perpendicular to the two supporting ends. I see the figure, such that slab core is the one-way slab. This is the definition of the one-way slab. Also, the slab is supported on the all four edges, and the ratio of the longer span to the shorter span. This is the longer span, and this is the shorter span. If your slab is supported on the four slab, and this is the longer span dimension, and divided by shorter span dimension is the greater than 2, your slab is the one way. Parallelly the span across the shorter span. This is the definition or a basic criteria for the one-way slab. Such as the slab are also designed as the one-way slab. In this case, the main reinforcement is provided along the spanning direction to the resistant one-way bending. As you can see, bending direction is this. So our main direction of the main bar is the shorter span. We will provide the main bar in this direction, and in longer direction we will provide a distribution bar. As you can see, this is the simply supported is, this is the unsupported is, this is the beam strip. As you can see the deflection diagram of the beam strip, this is the cylindrical deflection, and this is the moment is positive moment, and moment directed supported on the two ends of the one-way slab. Next is the behavior of the two-way slab. In this, as you can see the figure 1, this is the figure 2. This is the deflection contour diagram, score step surface, and this is the two-way span action. How the two-way behave in loading distribution transformation. As you see, the behavior of two-way slab is trapezoidal. This divides the load in the whole four directions. Behavior of two-way slab. A rectangular slab supported on the four edge supports which span in the two orthogonal direction, and the deflection in the form of the dish or score is called two-way slab. This is the definition of the two-way slab. For the two-way slab, the ratio of the longer span to shorter span dimension shall be less than or equal to 2. If your longer span and shorter span is suppose 2 meter, this and this is the 2 meter, 2 by 2, this is the 1. 1 is less than or equal to 2, as your slab is two-way. This is the simply supporter, this is the deflection. As you can see, figure 2 is the behavior of the two-way slab. Since the slab resting freely on the all four sides due to the transverse load, the corner tends to curl up and lift up. As you see in the figure, the slab loses the contact over the some region. This is known as the lifting contours or lifting corners. These slabs are called two-way simply supported slab. If the slab are cast monolithic with the beam, the corner of the slab are restrained from the lifting. These slab called are a restrained slab. As the corner, the rotation occur in the both direction and cause the corner to lift. If the corner of the slab restrained for the lifting or downward reaction result at the corner, and the end strip get restrained occur the rotation. Next is the, however, when the end are restrained and the rotation of the central strip still occur and causing the rotation corner, slab is acting as a unit. and the end strip is subjected to torsion. This is not very important, and this is the important type of the two-way slab. Two-way slab are classified in the two type based on the support condition: simply supported slab and restrained slab. First, we will show the simply supported slab. For the two-way simply supported slab, the bending moment mx and my, moment in the x direction and moment in y direction. For the rectangular slab, simply supported, all four is with the corner free to lift, and slab do not having the adopt the provision to prevent the lifting or corner are obtained. This is the formula, and this is the load on the slab. This is the span L. Uh, this is the square of the Lx square. This is the mistake, and this is the coefficient. This coefficient you have to obtain from the IS code provision. As you can see, where the alpha x and alpha y is the coefficient given in the table 1, table 1 and table 27 of IS 456. As we see, this is the table from the IS 456. Bending moment coefficient means alpha x and alpha y value given as per the IS code provision. This is the Lx by Ly, means longer span direction upon shorter span direction ratio. You have to interpolate the value, and you will have to derive the alpha x value and alpha y value. And 50% of the torsion steel provided at the mill span can be curtailed 0.1% of the Lx or 0.1% of the Ly from the support. This is the provision of the torsion reinforcement for the curtailment rule. And next is the two-way restraint slab. When the two-way slab are supported on the beam and when the corner of the slab are prevented from the lifting, and the bending moment of the coefficient are obtained from the table 2, as you can see in the also given in the 456-2000. For that, the depending on the type of the panel shown in the figure 3, as you can see, these are the whole type of the panels. The coefficient are obtained using the yield line theory. Since the slab are restrained and negative moment arise near the support, the bending moment are obtained using, this is the negative bending moment and positive bending. You will have to obtain both negative and positive in x direction. Also, you will have to obtain in the y direction. These are the, if your panel is interior, also the one short is discontinuous. Also, the one long short is discontinuous. Two existing is discontinuous. Two eads short is discontinuous. Also, the discontinuous eads. This is the continuous eads. This is the discontinuous. This figure. This is the four eads. All conditions are given for the slab. The different boundary condition of the restraint slab. These are the all slab panel names. This is the 1 panel, 2 panel, 3 panel. This is the 4 panel. This is the 5, 6, 7 and 8. These are the all divided. As you can see, if you have to learn, you can pause the video and learn the different boundary condition of that slab. For all that slab, this all coefficient are given in the IS code table number 16, 456. From that, you will have to obtain the alpha values. From that, all the value you will have to interpolate. First, you will have to find the support condition or type of the panel. From that, you will have to derive the Ly by Lx. If your Ly by Lx is 1.1 and your panel is interior, this is the alpha x value, this is the alpha y value. You will have to consider from that. This is the detailing requirement as per the IS 456. For that, the slab are considered and divided in each directions in to the middle and the end strip as shown below. We will see after that. The maximum moment obtained using the equation are the applied only on the mid strip, and 50% of the tension reinforcement provided in the middle strip and mild strip extend to the lower and within the 0.25 L of the continuous eads and or 0.20 of the discontinuous ead Remaining 50% will be inserted in the support. We will see in the figure if you have to understand. After that, we will show in the figure so you can understand better. As you can see in the figure, this is the reinforcement detailing and strips in a two-way restraint slab. This is the LY is our longer span. This is the LX is our shorter span. This is the torsion reinforcement given on the corner side. This reinforcement is given as Lx by 5 and this direction is Lx by 8. This is the strip, one strip, and in that we show this is the yields, this is the yield strip, this is the yield strip, and these are the our area of tension bars. This is the one bar is our throughout bar and second is our cutter bar. We will design as same. One is through, one is cutter, and same in the y direction, same in the x direction. After that, these are the all criteria for the moment and shear coefficient. For you have to design the bending moment and shear for coefficient for the continuous slab. If your slab is continuous, we will see in the next. Now we will see the one example of the design of the simply supported one-way slab. This is the design a simply supported one-way slab over a clear span. Span is given 3.5 meter and it carry the live load is given also 4 kilonewton. Also for floor finish 1.5 kilonewton and the width of the supporting wall is given. Supporting wall width is 230 given. Also add up the concrete grade is M20 and the steel grade is a Fe415 steel. First, you will have to assume the depth. For that, we will trial the depth and the effective span. First, as we assume the approximate depth, our slab is simply supported, though as per the codal provision, simply supported for that the depth is equal to span by ratio. Ratio means 26 from the highest code provision. For that, our span is also known. Span is 3.5 meter. You will have to convert in mm and divide by ratio. As you can see, our depth is coming 134 mm. For this is the effective. We will have to assume the overall depth. Overall depth equal to 160 mm. For that, we will assume the 50 mm cover full by explosion condition. For that, 160 our is overall depth, cover is 50 mm minus. We will use the 10 mm dia bar for the detailing. If divide by 2 means we will cover this from the our center of the slab. Equal to our effective depth is 140 mm. And after that, we will find the effective span. For effective span, two criteria is given. First criteria is effective length plus width of the support. Second criteria is effective length plus the effective depth of the support. Effective depth. Our effective depth is 140 mm. Width of the support means width of the wall is 230 mm. Our span is 3.5 meter. So it comes 3.73 meter and 3.64 meter. For the effective span, we will have to consider the minimum of both. So the effective span is 3.6 meter. After that, we will calculate the load on the slab. First, self height of the slab. For the calculation of the self height of the slab, you will have to consider the depth of the slab into density of the slab. So the first self height of the slab 4 is coming kilonewton per meter square. After that, floor finish is 1.5 is given in the sum 8 slab. Also live load is given is a 4 as you can see in the example. So we will have to sum of these three. The summation of the three is 9.5 kilonewton per meter square. After that, you will have to consider the factorial load. For that, ultimate load WU equal to, you will have to multiply by 1.5. This is the factor of safety for that particular concrete slab. You will have to multiply 9.5 into 1.5, so 14.25 comes kilonewton per meter square. This is the load on the slab. After that, you will have to find the bending moment of the slab. As our slab is simply supported, though bending moment formula of the slab is WL square by 8. For the MU is equal to WU L square by 8. As we will derive the W from this 40.5. Our slab means L effective is 3.64. This is the 6.64 square upon 8. So 23.60 kilonewton per meter is come. So the minimum depth, this is the check for the minimum depth. For that, the formula from the code of the minimum depth is the mu is equal to 0.138 FCK B D square. From that, you will have to derive the D equal to under root mu upon 0.138 FCK B. B is considered as the 1000 mm. We will design all slab as the 1 meter per 1 meter. For that, mu is given as 23.6 kilonewton. We will have to consider and convert in the Newton per mm, so that we will multiply 10 into 10 raised to 6. For that, 125 mm into our concrete grade is M20. For that, 20, and B is designed as a 1 meter. For that, 1000 mm. It's come 92.4, and our effective depth is 140. 140 is greater than 920, so our slab is okay in the depth criteria. After that, we will design the area of reinforcement. For that, we will find first. You will have to find the mu. For the finding of mu, this is the formula. You have to remember, or you have to write in your notes. Mu is equal to 0.87 Fy ASTD in bracket 1 minus Fy AST upon FCK BD. B is the width of the slab as 1 meter is considered. D is the depth of the slab. FCK is a concrete grade. Fy is a steel grade. AST is the area of steel, and mu is the moment as we derived earlier. 23.6 is the our mu. We will put all the value in the this formula and derive. Just a minute. As you can see, all the value putting in the formula, we will have to find the AST from this equation, and from this equation AST is come 504 mm square. Also, you have used the direct formula. As you can see, both answer is same, 505 mm. First, you will have to find the spacing of the slab. For that, the spacing formula is the area of one diabar upon area of derived from this equation into 1000. You will have to spacing criteria 140 154 mm. This is the our spacing, so that we will provide the 10 mm at rate 150 center to center. As you can see, this is the lesser than 3D or 300 mm. For that, 3D 3 into our defective depth 420 come, or 300. This is the okay for the spacing criteria. And we will see our provided PT. We will derive this PT from this 10 mm and the rate 150 center to center. As you put all this value in this equation, you will derive the mm square. From that mm square you will derive the pt is equal to 100 as over bd. Okay, and after that you will have to provide the distribution steel we will provide 0.12 percent of the cross section area. Our cross section area is the b is the 1 meter and d is the 160 mm. For that 0.12, this is the percentage you will have to convert in the divide by 100, and 192 mm square is come. For that 192 mm square we will first derive, we will use the distribution diabar of 8 mm, and for that 8 mm the area is 50 mm square, which means area of 1 bar divided by all mm square into 1000, the 260 mm square is come. So we will provide 8 mm diabar at the rate 260 mm center to center, and our 5D and 450 criteria is also satisfied. After that all the checks are come. For the checks of shear and checks of deflection and shear, for design you will have to find the design shear. If this is the design shear formula. For design shear, Vu is equal to Wu means WL by 2. This is our W. We will find this W from that particular equation into W is as the slab is given. Our W is divided by 2, means our total W is 500 from the previous equation. So that from that you will find the design shear is 25.93, and we will also have to derive this tau v value. Tau v is Vu by Bd. This is the Vu value. You will have to convert in the Newton per mm square. For that you will have to multiply by 10 by this is divided by 1000 divided by 140, and tau c max as per the code. Yes, this is given also in the code 2.8 kilonewton per mm square. Our slab is okay in the one way, in the shear. After the checking of the shear, we will have to check for the, this is the shear, also the shear criteria. If you this criteria satisfied, also this criteria is certified, you will have to just multiply tau c with the k is the factor derived from this clause 14.2.1.1, as this is the given in the code. As you can see, tau cd is the greater than tau v. Our slab is okay in this year. After that you will derive the you will have to check the deflection. For deflection criteria, the span by d for the axial span is less than the span by d allowable, and allowable span by d equal to L by d basic span into k1 into k2 into k3 into k4. These are the all factors. K1 is the modification factor for the steel, K2 is the modification factor for the compression steel, K3 is the modification factor for the T section span exceeded 10 meter, or uh, 10 by span. As per the clause of the IS code, the K1 is derived as per the codal provision. This K1 is 1.38, and also PT is given as we derived earlier. For that you will have to multiply the span by d is a 20. This is the 20, and K1 is a 1.38, and these all are 1. So 27.6 is come, and allowable limit is span by 140. Our span is this, and 140 from the IS code provision. This is the 25.92. So our slab is okay in the deflection. Next is the development length check. This is the development length formula. LD is equal to 5 into sigma s upon 4 tau CBD. Tau BD is a design shear strength. As our LD is equal to, we will consider 5 is equal to 0.87 into Fy, and sigma is also given as a 10 divided by 4. Tau CBD means 1.2 into 1.6 is equal to 470 mm. As the simple support where the compression reaction coefficient bar, the limit of dia bar is this formula. From this formula, LD is less than 1.3 m1 by V plus L0. Since the alternate bar are also the crank, so the m1 is equal to mu by 2. This is the 11.8 is considered. Also the V1 is given 5.93. Also the provided 90 mm dia bend, 25 mm spacing. For that L0 is provided 120. However, this is the okay in the development length. Also we will show the check for the cracking. In steel is more than the 0.12 mm cross area, and the spacing of the steel is also less than the 3D, and distribution bar is also used. 160 divided by 8, 20 mm dia bar is checking. Crank is also satisfied. As this is the detailing part, we will earlier see. This is the section BB. Section BB plot from that. As our slab is designed in all 4 directions. As you can see, this is the our main bars. This 10 torque 150 mm, as you see in this direction, short direction. This is the one throughout bar. This is the alternate bar. This is the top bar, and this is also alternate bar. And you can see this the dimension of that particular alternate bar is 360 mm. This is the 0.1 of the span, means 0.1 of this. Also you will have see this is the distribution bar. Also thickness is mentioned in this particular slab. This is the section A. If you cut this section, our main bar is shown in this, and distribution bar is also dotted, as you can see in the figure. Our main bar is placed in the below, and distribution bar is in upper side. And if you see in the this distribution bar is in lower side, and main bar is in bottom side, and distribution bar is upper part. And extra trope length we will provide it as a LD by 3, means L by 3. This is the L, and you have to divide by 3. This is your dimension of that particular slab. This is the design of the one-way slab. We will in next video we will see the design of the two-way slab. Thank you for the watching.